This is a flip video about heating curve problems. So we already learned about what heating and cooling curves are. So now we're actually calculating and doing problems that gives us values of how much energy is needed to do whatever process we are doing. So heating and cooling work the exact same way. So let's take a look at this problem. You have 42.3 grams of ice. So you're starting off as ice. That's important to note that because sometimes you don't start off as ice. It's heated from negative 20 degrees Celsius to 150 degrees Celsius. What is the total amount of heat needed for this process? The first thing you always want to do is you want to start off with a graph. So that's step one, is to make a graph. So if you notice I already started my graph here. Let's just fill in the rest. Okay, well if I'm starting with ice and I'm going all the way to 150 degrees Celsius, okay, and I'm talking about water in this instance, right, ice referring to water. So if that's the case, then I'm going to go from a solid all the way to a gas. 150 degrees Celsius I know is more than boiling. So I've got the 5 segments. 1, 2, 3, 4, 5. Solid, solid to liquid, liquid, liquid to gas, gas. Next, you have to label, notice how I have my axes labeled with the units in parentheses and a title. Next, you have to label some important temperatures. So on this axis, remember, you have to memorize that water goes from a solid to a liquid, which is melting at 0 degrees Celsius, and a liquid to a gas, which is boiling or evaporation or vaporization, right, at 100 degrees Celsius. What's this down here? Well, if you notice in the problem, I have to look. We're starting at negative 20 degrees Celsius. So negative 20, right, below 0. And how about the top? Well, we're going all the way to 150 degrees Celsius. So note, there will always be 4 temperatures you have to put on this axis here. As for time, it doesn't really matter because time is just going by. So the question's asking, how much heat do I need to melt this solid all the way to a gas? How much heat? Each step has its own heat. This step will have a heat, this one, this one, this one, and this one. Let's label our steps. 1, 2, 3, 4, 5. Okay? So we're going to start now, and I'm going to show you how to organize your steps. Please make sure that when you do these problems, you organize them in the same fashion. All right. We're going to have 5 steps. Here, we're starting off with the first 2 steps. So let's check out those first 2 steps. Here they are. Step 1 is a solid. So let's fill that in. Solid. Okay? If step 1 is a solid, it goes from here to here. I notice that my temperature is changing. Since my temperature is changing, I'm using Q equals MCAT. Q equals MCAT. Okay? So always on this one right here, the rising, anytime you see a temperature change, you've got the Q equals MCAT because it's a temperature change. All right? Remember, temperature change is calculated by taking the final minus the initial. If you remember, we're heating, so we're going this way on the curve. Right? That way. We're kind of going up the curve and heating it. So my mass, from the problem, is 42.3 grams of ice. That's going to be my mass all the time. We're not losing any of the mass. We're just changing its phase. So 42.3 grams. My C, if you remember, on the previous video, I gave you the specific heat capacities of water at different phases. This is solid, so I use the 2.06 joules over grams degrees Celsius. You will not have to memorize these. And now my temperature. Again, we said change in temperature is the T final minus T initial. So let's look at my graph. I start off at negative 20, so that's my initial, so negative 20 degrees Celsius. And my final temperature is 0. It's important that you subtract these in the right way. So it's 0 minus negative 20, which gives me positive 20. Negative, right, and a negative make a positive 20. That 20 had a decimal at the end, so I'll keep my sig figs. Okay, grams cancel out with grams, degrees Celsius, degrees Celsius. This is a good time to pull out your calculator and calculate this. We never look at a constant for sig figs. There's 3 sig figs here, but 2 here. So my answer needs to have 2 sig figs. Okay? All right, segment 2. Here's segment 2. You work your way up. A solid to a liquid. So this is a solid to a liquid. Is there a change in temperature? No. So I use this equation, Q equals M times change in heat of fusion. Remember, melting has another name, and it's called fusion. So that's what I use on step 2. I start off with my same mass. My mass will never change. Here it is, 42.3 grams. Now I'm going to take that solid and I'm going to heat it to a liquid. So since the temperature is not changing, that heat is being used to turn or change the phase. And if you remember from our video last time, here are our heat of fusion and vaporization for water. You will not have to memorize these. So I'm on the fusion step. Remember, fusion is melting, and I use the 334 joules over grams. Grams and grams cancel out. I never look at a constant value or a given value for my sig figs. So I have 3, so I'm going to need 3 sig figs. Pull out your calculator and get an answer for segment 2. Okay? All right, moving on. We are now on segment 3, seen right here. See, if everything is labeled, it's easy. In segment 3, it's a liquid. L for liquid. Is the temperature changing? Let's take a look. It is. It's going up. Okay? So with that being said then, I have T final minus T initial, don't forget. What's my specific heat capacity? Well, let me take a look. I'm at the liquid phase, so I use 4.184. Notice the C changes, joules over grams degrees Celsius. Now to do my temperature, let's see my graph. I start off at 0, so that's my initial. So TI is initial. And I go all the way to 100 degrees Celsius. So it's 100 minus 0. Well, that's 100 degrees. Don't forget, all of my temperatures had that decimal point at the end, so I'm going to keep my sig figs. Okay? All right, grams and grams cancel out, degrees Celsius and degrees Celsius, so my answer is left in joules. I have 3 sig figs here. I have 3 sig figs here. Don't look at the constant. Your answer needs to have 3 sig figs. Please calculate that on your calculator. Okay, segment 4. Here is segment 4. It's the 4th one. It's a liquid going to a gas. There's no temperature change, so what's happening? Boiling. Boiling is the same thing as vaporization, heat of vaporization. Remember, I'm using my same mass, but now I need to go and find my heat of vaporization, which is a constant. These will be given to you. Here it is, heat of vaporization, 2,260 joules over grams. Grams and grams cancel out, left with joules. Don't ever look at a constant for sig figs. Since there's 3 sig figs here, your final answer is going to need 3 sig figs over there. And lastly will be segment 5. Okay? In segment 5, if we look at the graph again, in segment 5, we're basically going from this point right here all the way up to the end, which is 150 degrees Celsius. Again, how did I know that? Because in the problem, it said we're going to 150 degrees Celsius. So in this last part here, again, it's Q equals MCAT because the temperature is changing. So I use my same mass. My C, remember I'm a gas. I need to find my specific heat for a gas. For water is 2.02. You will be given these constant values. And now my change in temperature, remember, is T final minus T initial. So let's assess that. If you've made a good graph, this is easy to do. So I initially start right here at 100 degrees Celsius. So that's my initial. Don't forget, all of my temperatures had decimals at the end. And my final was 150. Go all the way up to 150. Again, if I look here, 100 to 150, this segment right here, okay? Subtract those and I get 50 degrees Celsius. Don't forget, keep the decimal. And then this has only 2 sig figs. Even though this one has 3, I never look at the constant. My answer should have 2 sig figs. Take out a calculator and calculate that. And now, the last part of the question, if we go back to it, it says, what is the total amount of heat needed? Well, whenever you have a total, you add things up. So if you remember, I had 5 segments. I'm going to take the Q from segment 1, that's the energy needed for segment 1, and add it to the Q of segment 2, and so on with segment 3, 4, and 5. So if you notice here, I've kind of written you a note. The total energy is equal to all of the Q's added up with correct sig figs. That's the end of the flip video.